The Koch Snowflake by Sydney Hoffman. First off, this is called the Koch Snowflake, and it is a fractal. A fractal is a curve or geometric figure that displays self-similarity on all scales. If you were to zoom into a fractal under a microscope, it would look the same as if you were looking at it normally. The Koch snowflake was discovered by Swedish mathematician Helge von Koch. To understand Koch's snowflake, we must first look at his curve, which he came up with first. The Koch curve begins with a straight line that is separated into 3 line segments. The middle line segment is then replaced with 2 sides of an equilateral triangle, and this continues all the way to infinity, creating a curve. Instead of starting with a straight line, the Koch snowflake starts with an equilateral triangle. The steps to creating the curve are then repeated with each side of the triangle. For example, first draw an equilateral triangle. Then separate each of the sides into 3 parts and replace the middle section with another triangle without a base, like in the Koch curve. This is repeated over and over again to create the snowflake.
Wonder what happens to the snowflake's area and perimeter as it reaches infinity? Well, stay tuned to find out.
Since the snowflake is a fractal, there are many formulas that come with it. The first formula I'm going to discuss is the number of sides after each iteration of the snowflake. Since the original figure of the Koch snowflake is an equilateral triangle, we consider this the 0th iteration, and obviously we can tell that there are 3 sides. But you may be wondering, how do I figure out how many sides there are after 5 iterations, or 10? Well, I'm going to tell you. To figure this out, let's look at one side of the triangle. To make the next iteration, you cut this side down into 4 parts. Since this is repeated on all 3 sides of the triangle, the formula for the number of sides is 3 times 4 to the k, k being the number of iterations, as this fractal continues infinitely and the number of sides grow exponentially. So for the 5th iteration, we take 4 to the 5th and times that product by 3 to get 3,072 sides. And for the 10th iteration, we get 3,145,728 sides. In addition to figuring out the number of sides at each iteration, we can also figure out the length of each side in relation to the original equilateral triangle. Let's make each side of the equilateral triangle S. Since the next pattern in the fractal splits each of the sides into 3 parts, the length of each side in the first iteration is 1/3 of S. Then each of the S over 3 side lengths will be split into 3, resulting in the side lengths of each side of the second iteration will be 1/9 of S. The third iteration will be 1/27 of S, and so on. Each length of a side in the new iteration will be multiplied by 1/3. Since the lengths of each side in an iteration shrink by 3, the formula is S from the original triangle multiplied by 1/3 to the kth power, k being the iteration.
Now it's time for the big reveal. The Koch snowflake's perimeter is infinite, but its area is finite. The area is bounded by a limit, and no matter how large the perimeter gets, the area will not exceed a certain value.
Now let's find the formula for the perimeter of the Koch snowflake. Let's make each side of the equilateral triangle S like we did to find the number of sides, giving us a perimeter of 3S for the S sub 0 iteration. Since the next pattern in the fractal splits each side length into 1/3 the original, and there are 4 segments, the perimeter for one side is 4S over 3. Since this occurs on all 3 sides of the triangle, we multiply 4S over 3 by 3 to give us a perimeter of 4S for the first real iteration of the snowflake. The 0th iteration had a perimeter of 3S, and the first has a perimeter of 4S, so the perimeter grows by 4/3 after each iteration. Since the Koch snowflake's perimeter continues forever, and it is a fractal, meaning the pattern of making each iteration is continued, the 4/3 component of the perimeter formula is raised to the kth power, k being the iteration. For example, in the equilateral triangle, 4/3 is raised to the 0 power, making that part of the formula 1, giving it a perimeter of 3S, which we proved earlier. We then take 3S and multiply it by how much the snowflake's perimeter grows after each iteration, which is 4/3 to the kth power. Now here you have it. This is the formula for the perimeter of the Koch snowflake, and as you can see, the perimeter continues infinitely and has no limit. To find the area of the Koch snowflake, we need to look at the area for each iteration. Since the 0th iteration is just an equilateral triangle, we can find its area using what we know about 30, 60, 90 triangles. If we drop an altitude in the triangle, making two congruent triangles, we get that the angle at the base is 60 degrees and the other is 30 degrees. Making the side length of the triangle S, we get that the height is S root 3 over 2. Since the area formula for a triangle is 1/2 the base times the height, we get 1/2 S root 3 over 2 times S. This equals root 3 over 4 times S squared. To find the area at the next iteration, we would add the equilateral triangle's area we just found to the area of the 3 equilateral triangles added with the next iteration. Since we already figured out that the lengths of the sides decrease by 1/3 over each iteration, the next triangles have side lengths of S over 3. Since we already found the area formula for any equilateral triangle in terms of S, we just need to plug in S over 3 for S to get the area for the triangles added in this iteration. Doing this, we will get root 3 over 4 multiplied by S over 3 squared. This will give us the area of one of the 3 triangles added, so to get the total area in this iteration, we will take this and multiply it by 3 and add it to the area of the first equilateral triangle. To combine these two areas, notice how root 3s squared over 4 is in both of the areas, so we can take this out, giving us root 3s squared over 4 times 1 plus 3 over 9. For the second iteration's area, we need to add all of the new triangles added to the area from the first iteration. We also know that the side lengths of the new triangles will be S over 9 because it is 1/3 of the side length from the iteration before. Moreover, we already figured out that the formula for the number of sides is 3 times 4 to the k being the number of iterations. You can see from this that the number of sides goes up by 4 times after each iteration. Since the number of sides are going up by 4 and the triangles created are based on the number of sides, the number of triangles will also go up by 4. This means that 12 triangles, or 4 times the 3 triangles added in the last iteration, will be added to make the second iteration. Knowing this, the added area to the second iteration will be 3 times 4 multiplied to root 3 over 4 multiplied to S over 9 squared, where S over 9 was plugged into S in the original equation. Adding this to the first iteration we get, as you can see, there is a pattern emerging, where after each iteration's area, another 4 is multiplied in for the number of sides increasing, and another 1/9 is multiplied in because after each iteration, the side length is 1/3 the previous and 1/3 is squared. Furthermore, each time the number 4 appears, it is 1 less than the iteration number. For example, the second iteration only has 1 4 being multiplied to it, which is added to the previous iterations. This means that at any iteration, we add 3 times 4 to the k minus 1 triangles to the snowflake. Another pattern is that the number of times 9 is in the denominator is the same as the iteration number. So the second iteration has 9 squared being added to the previous iterations. Since in each iteration, root 3 over 4 is being multiplied to S over 3k squared and to 3 times 4 to the k minus 1, we get the formula to be root 3 over 4 S squared times 3 times 4 to the k minus 1 over 9 to the k. Since this is a geometric series, we can factor out root 3 over 4s squared to get the exact formula for the area of the Koch snowflake in sigma notation. In this formula, n represents the area after n iterations. To figure out what will happen to the area as it approaches infinity, we will have to replace n with infinity. Using the formula for a geometric series, we get after each iteration, the area increases by 4/9 the previous one, so we will place that as our rate. Using the formula we get, which simplifies to, multiplying this out, we get 2√3 over 5s squared, which is what the area converges to as n goes to infinity. As you can see, unlike the perimeter, the area is finite and will not continue forever. The limit of the Koch Snowflake's area can be seen by inscribing the original equilateral triangle in a circle.
Looking at the iterations, the snowflake will never reach outside of the circle representing the limit of its area.